First of all, on behalf of Midas IT, I welcome you all to this presentation of Midas FEA. This is how we are going to proceed. Firstly, we'll take a look at the overview, where we'll get to know why exactly as bridge engineers do we need Midas FEA. Next is geometry modeling, where we'll look at the modeling features and capabilities of Midas FEA, and we'll see how Midas FEA helps you model complex geometries very easily. After that, we'll be looking some powerful mesh generation tools which help you generate good quality mesh with ease in Midas FEA. After that, we'll be discussing the analysis capabilities, and we'll also be understanding why exactly and where are these analysis capabilities helpful to the engineers. Next, we'll be looking at the post-processing, the powerful post-processing tools of FEA, and we'll see how they are helpful to us. And after this presentation, we'll be going for a demonstration where we'll see some modeling and work process of Midas FEA. To begin with, I'll show you the configuration. In totality, this is all about Midas FEA. Midas FEA has a geometry modeler where complex geometries can be modeled quite easily. Next is the mesh generator, where we can generate the mesh for any sort of geometry. And in preprocessor, we have boundary condition and load definitions also, where we can define any sort of boundary condition and loads. We'll see how in detail later on during my presentation. Next is the after pre and post processors, preprocessors. We have the solver, where we have solver supported for 64-bit operating system with GPU accelerator, which enhances the analysis capabilities excessively. In the post-processing, we have powerful post-processing tools using which we can see detailed results, and those results can not only be seen in contour form, but also can be transformed into graphs and tables. To proceed, the first question that comes to our mind is, why should we use Midas FEA? The answer is here. Let's discuss some of the major application areas in bridges where Midas FEA is quite commonly used. First is the joint detail. Let's say my girders or beams are coming at this location and are connected in some sort of like this. This is the display of connection. If such is a joint, then we will be modeling in frame modeling software, say Civil. We'll be modeling these using nodes and elements. In that case, we can't get the concentration of stresses. At these joints, there will be stress concentration, and that cannot be obtained using frame modeling. For that, we have to go for finite element modeling and getting the exact stresses. Next is bridge connection. Generally, what happens is, like these steel trusses are rested upon this pier cap. At this location, there is high stress concentration, and these stresses cannot be obtained using frame modeling. So to get these stresses and to check whether this stress satisfies the limit or not, we have to go for finite element modeling. And in there, FEA comes into mind. Next is concrete cracking. In concrete cracking, FEA provides total strain crack material model, where we can define the non-linear behavior of concrete, and we can define the cracking pattern. What we get as a result is we can get the locations of smeared cracking, and we can also get the width of cracks as a result when we perform concrete cracking analysis. And this is very much helpful to the bridge engineers. Other application would be the pier deformation. Generally, when we talk about deep beams, Then in case of deep beams, solid modeling is very much necessary. If we go for frame modeling, then that's not that much accurate. So for accuracy, we go for solid modeling of deep beams, and that's the proper approach. And there, FEA is quite helpful to the engineers. Next is corrugated steel web bridge. Corrugated steel web sections can be defined in civil, but with some limitations. Plus, we cannot get the stresses at the corrugations, and corrugations are not that much detailed in civil as compared to FEA. When it's more detailed model, we get the detailed results as well. Next is steel and concrete girder. We can define steel and concrete composite sections in civil, but that's quite limited. For some sections only it's possible in civil, major ones. But let's say I have to model steel and concrete girder like this. Such a modeling can only be possible using Midas FEA, and in such modeling we have some detailed stress requirements which we can easily obtain using this software. Next is the curved steel box girder bridge. When the bridge profile is curved, then crucial results are distortion and warping stresses. When we go for frame modeling, then we ignore these stresses. Whereas in curved bridges, for getting these stresses from the analysis, we have to go for finite element modeling, which can be done in Midas FEA. Other example would be bifurcations of the web, like you can see in this picture. This web is bifurcating into two webs. If we go for frame modeling, then we just ignore the stresses at these bifurcations. To get the accurate stresses at these crucial locations, we need finite element modeling. Next is bolt connection. Generally, when we define, let's say, two sections, I sections, meeting at a particular location, then at the location of flanges, we just connect it using nodes in frame modeling. But that's too much approximate, because when we actually model the bolts in FEA, we can define the contact between bolts and these flanges, which would give us the accurate concentrated stresses at these locations, and which is very much crucial at such connections. Next application would be splay saddle in suspension bridge. This is actually the real-time project application from suspension bridge model using Midas FEA. From there, we have taken this example. Actually, what was happening in this case was this steel flange was piercing into this steel body, and there was high stress concentration which was exceeding the stress limits. If we hadn't modeled this using Midas FEA, then we cannot get these detailed stress concentrated stresses at these locations. Next application could be local buckling of orthotropic steel deck. Generally, when we go for frame modeling of orthotropic steel deck, then we can get the results, but these buckling results, local buckling in detail, cannot be obtained using frame modeling. The design codes do give some considerations for considering the buckling, but that's under approximate approach. For accurate local buckling stresses, we need to go for finite element modeling and hence FEA. FEA also provides CFD analysis. This is quite helpful when we have dynamic effects in case of bridge structures. Then we can model the section in FEA and analyze for computational fluid dynamics. After looking at all these application areas, it must be clear that how important FEA is and how useful it can be in our daily life projects. Let's see some real-time project applications. This is Von Nahm extradite bridge. For single pier, it was analyzed in FEA for detailed stresses, and dynamic analysis was also performed. Another application is steel arch bridge. For this bridge, only a portion of the bridge was analyzed in FEA for detailed stress concentration at these locations. Next is hanger clamp. Generally, when we go for frame modeling, we connect the hangers to the cables, main cables, just through nodes. But at these nodes, we have hanger clamps, and at these hanger clamps, there is high stress concentration. If we do not go for finite element modeling of hanger clamps, then we are just considering the clamps to be sufficient enough to resist the load. But that might not be the case and might lead to failure of the bridge. So this is very much crucial. Another analysis which FEA supports, and the application example of which can be seen here, is fatigue analysis. As you must be knowing, codes give provisions in design to consider fatigue, but that's another approximate approach. For exact stresses due to fatigue and to see the exact member which is failing due to fatigue, we need to perform the analysis for fatigue itself, and that can be done in Midas FEA. This is project application of CFD, project application of contact analysis. We'll see this in detail later on while discussing the analysis capabilities. And now let's take a look at the framework of the software. To show this, I'll move to the software itself and show you. Let me just open a model file. I have opened a plate model file just to show you how the software looks like. On the top, we have the main menu, which has the drop down feature, and the main menu is so user friendly. You can see, in order to model the entire geometry, mesh it, analyze, and then get the results, we just need to follow from left to right. That is, firstly geometry, we model everything, then mesh the geometry, analyze, and then see the results. After the engineers are well versed with these main menu options, we can go for these tabbed toolbars, which can be quite convenient and quick for modeling, analyzing, and getting the results. Next is the works tree of FEA. It's just like the Windows Explorer, where we can check everything. Like, let's say I want to check the material property, I can check it here. So it tells you the entire work progress and whatever definitions you have provided. Not only pre-works tree, but we have post-works tree as well, using which we can see the results. So after looking at pre and post-works tree, we have the properties window, where we can change these from the default options and modify the display that we want to have. Another feature is the output message window, which shows, like, let's say I perform the analysis again, and I can see the analysis progress here in the output message window. I can see if there is some error message or warning message during the analysis and take the adequate steps accordingly. Another good feature in FEA is this task pane. Task pane, actually we can see the recent projects that I used. I can also see different analysis types that are supported in FEA, and the advantage of this is, let's say I want to perform time history analysis. It will tell you what all definitions are required in the software, then we can solve from here, and then what all results we can check. Another is the user defined task pane. Here the users can define a task pane according to their choice and use it in their projects conveniently. Let's move back to the presentation. Next is the geometry modeling. Now we'll take a look how geometry modeling in FEA is helpful to the engineers. When it comes to modeling, engineers are always looking for data exchange. That means import and export. Let's see all these features in the software itself. As far as import and export are concerned, FEA supports import from all these AutoCAD files. STEP, IGES, Parasolid file formats can also be imported. Good advantage for Midas family program users is that we also support import of files like Midas MXT. Let me show you how we can import the Midas MXT file and how it's helpful for engineers using Midas Civil. I'll just open a civil file. This is my bridge model with the piers and all the deck model, and I have all these load cases defined. I'll go to export MXT file for FEA, and I can just save this file. I can close civil now, and in here I can import. As you can see, the entire bridge model has been imported along with the property definitions like beam, plates. All the loadings have been imported and the boundary conditions also have been imported. We can see these here like properties, 1 dimension for beam, 2D for plate, and these are the point springs. We have all the materials imported in FEA, boundary conditions are imported, all the load cases have been imported. You can see force load, nodal force, temperature load, pressure load, all sorts of load can be imported, and we can show or hide from here. After taking a look at this, let's move back to presentation. For export, FEA supports export to STEP, IGES, BREF format, and files can be exported to Civil and Gen as well. Next is the data exchange between Civil and Gen to FEA. Actually, if we take a look at this model file, beams have been imported as 1D elements and 1D property has been assigned. What if the frame model from Civil is to be imported as solid? In that case, we have another option. Let's see that. This is my PSC bridge along with all the tendons. I will export this geometry to FEA as solid. You can see this is a frame model right now, line beam. I will export this. To export, I go to File, Export, and Frame to Solid. I can choose all the tendon profiles and all the girders, save it. Now we can close this file. In FEA, let me just open a new file. File, Import. Sorry, for importing frame to solid and frame to plate, we have this option here in the geometry. We go to frame to solid. We select that frame to solid file. Depending upon the length of bridge and the tendon profiles that have to be imported, it can take a while. Actually, in this bridge model, the geometry is not very complex, but the tendon profiles have to be imported and it can take a bit of time. Let's wait for it to be done. Okay. Now you see entire geometry along with the tendon profile is imported in FEA. We can mesh the geometry from here itself, or we can mesh it later on. I'll mesh it later. Now click OK. To see the tendon profiles, let's hide this solid or change the display to wireframe, and now we can see the tendon profiles which have been imported, and we can define these at tendons, mesh the solid, define the boundary conditions, loads, and analyze. So it's that simple. Now when we talk about geometry modeling, Civil also has geometry modeling capabilities, like we can model points, curves, surface, solid, transformation is possible, but all these are with some limitations compared to FEA, whereas FEA has some additional features like feature generator, feature modifier, repair of geometry, which is not at all available in Civil. Using these features completely fully supported in FEA, we can model any sort of complex geometries that you see at the bottom very easily. I'm not going into much of detail. Let's take a look at the advanced modeling capabilities of Midas FEA. One would be extrude, that is we have the plate profile, we just extrude to generate the solid. And there could be, we sweep the profile along the guide curve to generate such a curved bridge profile. This profile could be rotated about vertical axis to generate such a profile. To generate tapered section, we can just loft from one section to another and we can get the tapered section. It's that easy. Other advanced modeling features would be like offset, chamfer, fillet, solid to shell conversion. So these are quite handy when we are modeling complex geometries. Now mesh generation. When we talk about mesh generation, we have mesh of node, meshing of linear elements, and meshing of planar elements supported in Civil, and those are fully supported in FEA, but we have some additional options in FEA which make meshing of complex geometries very easy, and we'll get to know in this presentation how accurate the meshing capabilities of the software are. Let's proceed. Auto mesh in Midas FEA is quite an intelligent feature. By intelligent, I mean when we auto mesh the solid, like this solid, it automatically adjusts the mesh size at these locations to finer mesh and provides a smooth transition. So this can be really time-saving feature. Otherwise, engineers would be needed to define the seeds manually. That's too much time consuming. Another advantage in FEA is automatic surface meshing. That is, when we import complex 2D geometries, then it's really helpful, this feature. We can directly mesh this plane without defining a surface here. We'll see this in the demonstration. Next is mesh protrusion. FEA also supports CAD-based features in Midas, CAD-based features for mesh, not only for geometry but for meshing too. So profiles like these, we don't need to generate the geometry actually. We can just sweep the mesh along this curve to get this profile. Likewise, we have revolve, fill, extrude. Now another important thing in FEA is reinforcement elements. Non-linearity of reinforcement elements can be considered in FEA, and to model the reinforcement, FEA provides two methods: embedded rebar and truss with interface. In first method, the rebars can be defined as embedded bars and they don't need nodal connectivity as shown here. The other method is to model the reinforcement as truss element with interface defined all along it. For that, for the second method, we need to have the nodal connectivity. So the engineers could choose which method they want. Embedded bar is the most commonly used one. Not only meshing the geometries, but being engineers, we all know how much nodal connectivity is important in mesh geometry. For that, FEA provides us the option to check our mesh where we can see free edges, free faces, and we can find if some nodal connectivity is not maintained, and we can take adequate steps to modify our mesh. Quality assurance, this can also be checked in terms of these parameters, and we can see if our mesh is of good quality or not for better results. After meshing, let's take a look at the analysis capabilities of Midas FEA. Before we move on to analysis capabilities, we'll take a look at the equation solvers provided in FEA. There are two solvers, direct solvers, iterative solvers. Iterative solvers are very much helpful for large scale models with and some specific nonlinear problems, whereas direct solvers are generally used for simultaneous linear equations. Amongst these, multifrontal solver is the most commonly used one. For this, we support 64-bit operating system with GPU acceleration, which enhances the analysis capabilities by 3 to 6 times compared to 32-bit operating system. Now let's compare the analysis capabilities of Civil and FEA. Midas Civil provides all the top 7 analysis capabilities, and those are well supported in FEA also, but there are some additional analysis capabilities in FEA like interface nonlinearity, reinforcement nonlinearity, cracking analysis of concrete, contact analysis, heat transfer, heat of hydration, fatigue analysis, and CFD analysis. Let's see these analysis capabilities in detail. Static analysis. Just like civil, in FEA also we can form load combinations for the multiple load cases that we define. FEA also supports eigenvalue analysis, buckling analysis. The advantage with finite element modeling is that we can know the positions where global and local buckling are taking place, and we can actually see the locations of local buckling as shown highlighted in this figure. FEA supports dynamic analysis as well, like response spectrum analysis and time history analysis. Just like civil, FEA also has design spectrum database for response spectrum functions, and for time history we have 54 earthquake acceleration records which we can use or we can define ourselves. These tables for defining the functions are well compatible to Excel, so we can just paste from Excel. Material nonlinear analysis. Von Mises, Tresca, Morculum, Drucker-Prugger, Rankine. These are all supported in civil, but FEA supports user-supplied material as well. The advantage with this material is that if some material nonlinearity function cannot be defined using these material models, then the users can write their own file which can be entered into the software, and material nonlinear analysis can be performed with this material. Another is geometric nonlinear analysis. These are the methods supported, and iteration methods are just like material nonlinear methods. Interface nonlinearity analysis. This is really crucial when we have two materials of different stiffness. Then interface is most commonly used and very crucial in Midas FEA. We support discrete cracking, dilatancy cracking. This could be used for concretes being casted at two different ages. We also have Coulomb friction and nonlinear elastic, which is most commonly used for steel concrete interface. FEA also supports combined cracking, shearing, crushing, which is used for masonry models. So any sort of interface can be simulated in Midas FEA. Heat transfer analysis. In this, we can define steady state heat source or transient heat source temperature variation. So both the analysis can be performed. Heat transfer in FEA takes place through conduction and convection only. Heat of hydration analysis, you must be thinking that it's supported in civil as well. But the thing is, in civil, we can model the solid elements, but reinforcement cannot be defined in solid elements. And as being bridge engineers, you can know that sometimes it's very much necessary for mass concreting structures to define the reinforcement and then perform heat of hydration analysis, just like pier cap. Next, we provide contact analysis, which is generally used for suspenders. Here is a lug with two plates and a pin. This plate is in permanent contact with lug, so we define a welded contact in FEA. And here the pin is in general contact, that means pin can slide in this hole, so we define a general contact between pin and the plate and lugs. The advantage of modeling this contact is that we can actually get the forces and stresses at the contact surface, which is very much crucial, and we can compare it to the limitations of the forces and stresses and check whether it's safe or not. As I mentioned, FEA supports cracking analysis, which is helpful for engineers to actually find out the locations where cracking would be occurring under the applied loadings. FEA in the results provides crack pattern using the disk plots. Crack width is calculated using this formula. Engineers can check the crack width compared to the codal limitations and see themselves if it's within the limits or not. FEA also tells you the element status. We'll see this in the demonstration module. Another analysis capabilities in FEA is fluid dynamic analysis. Let's say I have this bridge model. I model the section in FEA, apply the dynamic wind load. From the CFD analysis, we can get the pressure acting on this section. We can get the vortex formation and we can get the aerodynamic coefficients. The last analysis type that I am talking about is fatigue analysis. In FEA, we can not only define the load history but also input the SN or EN curves according to the codes and perform the fatigue analysis. The advantage is we can actually find out the location where the fatigue failure would be taking place. In the results, we get cycles to fatigue failure and the damage. After analysis capabilities, let's take a quick look at loads and boundary conditions. All sorts of loads and boundary conditions can be defined in FEA. The advantage of FEA compared to civil is that here we can define loads not only in Cartesian coordinate system but cylindrical coordinate system also. So if we have some curved profile like this, then we can define the loading in circular coordinate system along the radius. Likewise, if we have some loading varying along the vertical height, then we can actually define the profile in curve and apply the loadings. So any sort of loads and boundary condition definition is possible. Another advantage with FEA is that we have arbitrary loading. That is, we can define the loadings without any nodal connectivity requirements. After taking a look at all these analysis capabilities, let's move on to post-processing results. If you see this table, you can find out that there are some post-processing results of FEA which are not at all available in civil. Actually, these are the advanced post-processing powerful capabilities of FEA, and because of these, it makes FEA quite convenient for complex geometries result giving. Let's see these capabilities. When we talk about post-processing results, we can not only see results in form of contours, but tabular format also. These tables can be exported to Excel and graphs also. Exact deformed shape. By exact deformed shape, I mean when we go for frame modeling, we get nodal deformations. But in FEA, when we are going for solid or plate modeling, then we get the exact deformation at every location. So that's very much crucial in structures like these deep beams and the structures on the right. Isosurface plot, that is plots with same values are highlighted. Clipping plot, this is quite helpful. Let's see, I have a tendon group. Then from the surface, we can't say that stresses are too high. Maybe they might be within limits. But if we clip the surface and we check the stresses inside, then the stresses might be exceeding certain limits and might be failing. So this clipping plot is very much helpful in checking the results on the inside of the curve or geometry. Next is mirror plot. In case of symmetrical geometry, this is a time-saving feature. We just analyze half of it and mirror the results about this mirror plane to get the complete picture. Vector plot, we can see the results in form of vectors. On curve diagram, we can define the curves on the geometry itself or along the edge to get the results all along that curve. Result tag, this is quite helpful either to display the results or to check the results at the nodal positions. We can tag the results and check the actual values. Legend control. Legend control, like civil, we can change these legends from scientific to fixed. But not only that, we can also adjust the range and also the color that we want the results to be displayed in. That's all about the post-processing results. Let me tell you something about our user support. We here at Midas believe in keeping our users happy, and for that we have some additional benefits. That is, we have Q&A board where users can send us the questions and we here as technical engineers help them in their queries and provide them suitable answers, which helps them not only to learn the software but also to get better results and make better use of our software. We also time to time we provide trainings, webinars for the engineers attending which they can gain some knowledge and make the better use of Midas FEA. Now I'll be giving you some demonstration of the software where we can see quick modeling capabilities of FEA, and then we'll check the results and then we'll end this session. Okay. Whenever we start FEA, this is how it looks like. Here we can change the unit. I want Newton and centimeter. Okay. I want to create a 3D geometry. Okay. I'll go to curve, create a circle, center at 0, 0, radius of 40. Again center at 0, 0 and radius of 100. After that, I'll create a line. I have to enter the coordinates. I'll input -60, 30 and the length is 120. Next is -60, -30. Length would be 120. Next is -120. I don't need to enter -120, 0. It's already understood. And the length of this line is 240 centimeters. After my geometry is created, I can go to geometry, curve and intersect. I can select my entire geometry and click apply. I can delete the unnecessary lines which I don't want. Just click delete from your keyboard and click OK. Now to mesh this, I have to define seeds. I'm doing this because I want to control the size according to my wish. So I'll define the seeds for these edges. Like I want these edges to be divided into 8 parts. So I'll choose number of divisions as 8, apply, and these edges to be divided into 4, OK. After this, I'll go to mesh, map mesh, key edge area. I do not need to create planes to mesh this. I can just select the edges and mesh this geometry. Element size 15 centimeter. I'll choose property of 1 for 2D and 2 for 3D. Click apply. You can see as I chose divisions of 4 here, there are 4 elements defined. Likewise, I'll mesh this entire plane. After meshing, you can see these are not meshed. To mesh it, I can just go to protrude and fill. I can use edge to 2D. I can choose bottom edge, top edge, number of divisions as 1, property as 1, apply, bottom edge, top edge, division of 1 and click OK. After my 2D geometry is complete, I can go to 3D modeling and protrude. As I said earlier, we don't need to model the geometry actually. We have these CAD based features in mesh. So I'll protrude, extrude this mesh. Extrude, select the direction, offset 20 centimeters, number of times, let's say 26. Now I'll change the view to top view and extrude these. Extrusion direction would be same, Z direction, and reduce it to 23. Apply. Now I'll extrude these plates, number of times 3. Extrusion direction would be same. Now you can see it was so quick to model this pier. Now I have to model the pier cap. To model the pier cap, I'll move the work plane. For that, I have this move work plane option. Let's see in isometric view. Translate and rotate. I'll input 520 centimeter, DZ of 30 centimeter, rotation angle 90 degree, and check the preview. Yes, this is what I want, so I click OK. Front view. Now I'll model the pier cap. I'll go to geometry, curve, polyline, wire. I will enter the coordinates 60, minus 60. Next coordinate is 180, 32. Next is 0, 28. next minus 180, 0, and then I can click on close and right click. So my profile is generated. I can click cancel, check the isometric view. To move this to the other side, I'll just use geometry transform translation option. I'll just select this object, select the direction, uniform copy at a distance of 60 centimeters, and then we click OK. After it's translated, I can go to Y and then move work plane. In move work plane, I'll choose translation rotation DZ of 520 centimeters. OK, and now it will work. Geometry, curve, work plane, and then I can create a profile. I click on here. This is my first node. This is my second node. Now I want a circular profile using 3 nodes. So I choose first and second. Profile is created. Now I want straight. Finally the curve is created here. And now I can define the mesh seeds. I can go to mesh and size control along the edge. I choose this edge and define a seed of number of divisions as 8. Click apply. Again choose this edge, number of divisions as 3. Click OK. Go to mesh, map mesh, edge area, vertical edge. Choose this face, define a property of 1 since it's 2D, mesh size of 10 centimeters. Click apply. Likewise, I mesh this face, same size, click OK. Now I'll go to mesh, protrude and sweep 2D to 3D. I select 2D mesh, I select the guide curve. It will be swept up to this location. Delete the original mesh. 3D, apply. Likewise, I can extrude this along selected profile. Same property, OK. Now after I have generated the right side pier cap, I can just mirror it. I can go to mesh, transform, mirror, and I can select the right side mesh sets and select the mirror plane. Mirror plane would be YZ plane, so I can select YZ plane and click OK. So this is how my pier cap along with pier is modeled. After the modeling, we have to define the property. We go to analysis, we define the property. Create a 3D property with ID of 2, just name it pier. Define a material. I'll define total strain crack material, elasticity 2.3 into 10 raised to the power 6, weight density 0.023536 Newton per centimeter cube, Poisson's ratio of 0.167, expansion coefficient, let it be 1 minus 5, and here we can choose total strain crack material model. Let's choose this one. Confinement effect, let it be none because I'm not modeling the reinforcements in the pier and pier cap. And here I can define the tension functions. Let's define it. Tension, object model, and let me enter the values. Now let's define a function for compression. Felt a value of 2240 Newton per centimeter square. For shear, let's define a constant of 0.3. Okay. I can choose the functions that I defined here. That will how these tension, compression and shear will vary. Now I can click OK. My material is defined. I can close this. I can choose the material here. ID is 2, that's for solid, and click OK. You can check the property here in the worksheet. It's defined to all the solids. So all the solids have been defined with total strain crack material. That is, crack analysis will be performed for all. After property, we have to define the boundary condition. We go to analysis, constraint. We define a load case, boundary case set. So I name it boundary condition. First, select the nodes. I select these bottom nodes and I choose pinned condition. OK. After boundary condition, I can go for defining the load. Let's define a load set for self-weight and for pressure load. To save the time of analysis, I'll just define two loads. Analysis, load, body force is a self-weight. I apply -1. Analysis, load, let's apply a pressure load on 3D element face. Change the view to front view. Select the face. You can see I've selected the face on the top. I can define normal direction, pressure load of 10 Newton per centimeter square, and click OK. After boundary condition and load definition, we go to analysis and we define analysis case. We add an analysis case. Let's name it total strain crack. For nonlinear material analysis, I need to choose this one. In here, to activate the mesh sets, we just drag and drop boundary condition. Similarly, loads. So all these are activated. We go to output control. We check which results we want to have. Analysis control. We can define which method we want to choose for nonlinear analysis. And let's say I want to have 5 steps for load and I want to terminate the analysis if there is some divergence. OK, OK. Now let's perform the analysis. Just save it. While the analysis is being performed, you can see the progress of the analysis at the bottom in output message window. Analysis, it's quick, but since we have defined 5 load steps, so it will take some time, not quite long. Iterations are being performed for the last load step, so very soon we'll be having our results. Everything is fine. Now let me just hide all the curves and then go to post processing. We have the results for all the load steps. We can see all the results. Let's see for the last load step. We have dx deformation result, dy, dz. All the deformation results are there. We have 3D strain results, strain in x, y, z and everything. We have all the stresses. Along with stress results, the important thing for which we define total strain crack is the crack status. You can see the entire top portion of the pier cap where the loading was applied. We have the phase as plastic phase. That's the strain is increasing in plastic range. So FEA indicates it using P, plastically open. And we have the stresses in normal, shear and tangential directions, and these disk plots show you that cracking is taking place at these locations. We have the crack width values as well. We can check the values, and that's all from my presentation. Thank you all for listening.